So today we'll start in on chapter 13 on oscillations, but I think what I want to do to start is do a little review question on Learning Catalytics. And unfortunately, I did not get a chance to put all these things into Learning Catalytics this morning. You have to cut and paste everything, and it's rather painstaking, so I did not do that, but you'll see on your Learning Catalytics, just choose A, B, C, D, or E. So it's one of these. So sorry it's not on your device, but basically, construction worker of mass MW, whatever that is, sits 2 meters from the end of a steel beam, and the steel beam has a mass of MB for beam. And you can sort of imagine the gravitational torque acting down. So this is actually an extended free body diagram for all these forces. And the two unknowns are actually the normal force from the wall on the beam and some force which I'm calling F1. It's a little bit like a static friction force, but anyways, there is some force acting on the left end of the beam, and it's diagonal, but we've decomposed it into two components, right? The normal force and the F1. So I'm going to ask you about those two forces, and we can define the axes of being, this is the pivot here. I'm going to define X that way, Y that way. So think about balancing torques, think about balancing the X components of the forces, and think about balancing the Y components of the forces. And if you can see the answer in there for the normal force, please click it in, and I'll give you a minute to think about that. So there are three equations. The sum of all the torques around that pivot is 0, the sum of the X components of all the forces is 0, and the sum of the Y components of the forces is 0. I think that you can actually figure out the normal force from just that the X components will cancel. So it's going to be N minus, if you do a little triangle there, I think it's T times cosine of 30 degrees equals 0. So I think it's E. And now let's think about F1. And the same thing, you won't actually see the question on your Learning Catalytics because I didn't type it in yet, but it's the same thing.
What is the force F1?
So it's again the force of the wall on the beam at the left end, but now what is the vertical component of that force? N was the horizontal component of that force. See if you can figure that out. I'll give you a minute. Yeah, so the way I would do this, I'm going to try just the Y components, so it's going to be F1 minus the M beam times G minus the FW times G, and then plus this component, the vertical component of the tension, so plus T sine of 30. All of that equals 0, so you can solve out for F1 is equal to, MB plus MW times G minus the sine. Yeah, so I think it's C. See where I'm doing that? So once again, there's always these three equations: balance the torques, balance the X component, balance the Y component. The first thing I usually try in these problems is the force equations: balance the X and balance the Y. And if those don't work, then you have to try to figure out the counterclockwise and clockwise and the lever arms, and it's sort of the second step. So, quick announcement. I wanted to let you know that there's these course evaluations up. So it is true that an essential component of our commitment to teaching excellence is regular evaluation of the course by students. So there was an email sent to you. There should be a link in your portal on evaluating all your courses. It takes about 10 to 15 minutes. There's a lot of little multiple choice questions. There's some free-form questions where you can type in an answer. Your answers and thoughts are anonymous, but they're important to me and important to Brian. When these results become available to us, which is after the final marks have been submitted, we will read every comment and, and think about it. The other thing that will happen is that these evaluations do get made public, at least the numerical part of it, and so other students will be able to see whether this course is sort of good or bad. And the other thing that happens is that every year we have a promotion through the ranks committee meeting that goes through and decides what happens to every professor and whether they get a raise or whether they get fired or something. And the course evaluations that you guys fill out are a big component of the data for those meetings. And so so our future is quite heavily determined by how we do on these things. So take them seriously, please. We do take them seriously. The deadline is December 7th. I have this bonus 1%. Everyone gets 1% added to their final course mark if at least 65% of the students enrolled in this course have completed the course evaluations. I'd like to be able to give you each a bonus for doing them, but it's anonymous. I can't figure out who did what, so this is how it's going to go. If fewer than 65%, then nobody gets the bonus. So try to encourage your friends. As of this morning, 11 a.m. section, 36% of you have already done it, and 37% of the 5 p.m. have done it. So I'll keep you updated on that as time progresses, and if we make it to 65, then we're golden.
Can I just prove to you that I did mine?
No, it's anonymous.
Yeah, I was just sauce.
You can't show me whether you did your evaluations. We need to get to 65. Last day, I asked this question, I don't know if you remember. Imagine you have a mass on a spring. This is sort of how we start any oscillations chapter, is we imagine a vertical wall with a spring on it and a mass attached to it that's on a frictionless surface. It's a little abstract, but if you pull the mass away, it stretches the spring. If you let it go, it's going to accelerate back towards equilibrium. The question is, when it gets to equilibrium, is it moving? And the answer is yes. So what's equilibrium? Equilibrium is, it's the spring's equilibrium. It's the position where the spring is exerting zero force on the mass. If you stretch the spring, it pulls. If you compress the string, it pushes. But right at equilibrium, it neither stretches it neither pulls nor pushes, so there's zero force. But if the object's already moving and the force goes to zero, does it stop? The answer is definitely no. It's got its own inertia, so we say it overshoots equilibrium. It's got some velocity there, it keeps going. Now, after it goes beyond equilibrium, it's going to be compressing the spring, so it'll be slowing down, but it's definitely going to go way past its equilibrium position. And this is how we get to simple harmonic motion. But even before we get to simple harmonic motion, I wanted to define frequency. And you may have seen in the pre-class video a Japanese fountain. So there's this, I don't know why I thought about this, but there's this great scene in a movie called Kill Bill in which there's these two ladies and they're trying to chop each other's heads off. It's a different story, but in the background there's this great fountain which it fills up with water and then it tips and then it dumps the water and then it goes back up and fills up with water again. So, and it's rather relaxing to watch it. So Kevin has brought one for me to just watch while I lecture. But you've seen a video of it on the pre-class. And the point is that this is not simple harmonic motion. What this is oscillating motion. It is something that moves in a way that repeats. And if you watch it long enough, you'll see it always does the same thing again and again in a predictable way. And you can measure the period, which is how long it takes for it to get back to a repetition, each subsequent repetition. So you could maybe make a plot of the end of that thing versus time, and you might see that if this is the height versus time or something, that it gradually, it's up, fills up, then it drops down, and then comes back up, something like that. Well, I guess it would have to be an exact repetition. And if you have an exact repetition, then T is the period between one oscillation and the next. It's called the period. And the frequency is just 1 over the period. And so oscillation frequency is measured in full cycles per second, and the word for that is hertz. The reason we call it hertz instead of just seconds to the -1 is because when we start going into equations for simple harmonic motion, we will find that it's convenient not to use frequency in hertz. We're going to use frequency in radians per second. We're just going to times it by 2 pi. So this is the oscillation frequency. So angular, there's no angles. That's for some reason called angular frequency of the oscillation. So again, it's kind of like mass in a spring, it's just going back and forth. It has some frequency in hertz. They times it by 6.28, and you get another way of characterizing the frequency called omega. It's a bit weird. But you'll see why, if we don't do this, then we end up with 2 pi's in all of our equations, or 4 pi squareds, and it gets really, the equations look ugly, and so we just do this trick, which is weird, but then it makes things simpler later. And here's the spring mass system. So this is now we're going to start talking about simple harmonic motion. This is starting this SHM. Okay, got a mass, got a spring. Hooke's law says that the force is linearly proportional to the distance, negative k times x, where x is the distance from the origin here. And this origin is defined as the spring equilibrium. Okay. And then F net equals MA. So this one is equal to F net is equal to negative K times X, and that's equal to MA. What is A? Well, A is the second time derivative of X. So you end up with this equation, if you solve it out, it's negative K over M times X. And that's sort of the typical simple harmonic motion equation, which is that you've got second time derivative of something, maybe X, is equal to negative of a constant times that X. Every time you see that situation, then ding, 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 you know you've got simple harmonic motion, and it always has a particular solution, which is cosine. So what you do is you just write it down. You say there's a trial solution. Just do the quick solution. We did it in the pre-class video, but the basic idea is X is equal to A times cosine of omega t. And then you get where A and omega are constants. Okay. And the question is, does it work? So we're going to say, oh, here's a solution. Was it the solution? I don't know, but we could just plug it in because we know how to take derivatives and just see if it works. It seems like a bit of a strange way to solve a math problem, but this is the way the mathematicians do it. So if it's good enough for them, it's probably good enough for us. So you go d by dt of x. So it's d by dt of the thing, our trial solution. A times cosine of omega times t. So you need to know derivative of cosine, which is negative sine. You've got to use a chain rule. So it's going to, you're going to pull out any constants. So it's going to be omega times negative sine of that same thing, sine omega t. Oh, and don't forget the a. So you end up with negative a omega sine of omega times t. So that's that's actually your v. And then your acceleration is your dv by dt, dvx, we'll call it that. And that's going to be equal to d by dt of that thing you just found, which is negative a omega of sine, omega t. And so again, chain rule is going to bring out another omega. Derivative of sine is positive cos, so you're still negative. So you get negative, there's an a, there's an omega squared, and you get cosine of omega t. And so you can rearrange that as equal to negative omega squared times A times cosine of omega t. But now, so that's A. You say, hey look, but that's x. And so, we say A of x is equal to negative omega squared times x. And so we solved it if and only if omega squared is equal to k over m. So that's important, that your omega squared is k over m. A is arbitrary. Doesn't matter. Okay, so that's the solution. You can plot it. It just looks like cosine. It's a bit weird because I don't know what adjacent over hypotenuse has to do with the mass on a spring. It has nothing to do with the mass on a spring. Right? Cosine is adjacent over hypotenuse. And this is, so what we're doing is we're just saying, okay, but it's also a button on your calculator, which takes omega t and converts it to cosine omega t. And so if we use that button on our calculator, we can predict the motion of a mass on a spring. So it looks like this. And I guess it does kind of make sense because you expect it to go oscillating back and forth. If you've ever played with a spring and you let it go, it's going to go boing, boing, boing back and forth. So maybe cosine isn't such a ridiculous thing because it does go back and forth. This is position versus time. You release it at position A, and then it goes back and forth. So A now has a meaning. A is the amplitude. That's where that comes from. I guess it's actually half the maximum distance it goes back and forth, because it goes from plus A down to minus A. So that's the name for that. It's in meters. So, and the basic idea, if you've got Hooke's law, it's negative kx. Acceleration is this net force over m. Then you expect that acceleration is negative k over m times x. So the acceleration is just the upside down of the cosine curve for position. Except now you have A max, where A max is this omega squared times A. To get those units right. So, to summarize, oh, yeah, there's another thing I forgot to put in here called phase. Yeah, so we'll do that. If the initial, so all this stuff assumed, if we look at the previous one, that you released it from rest at its maximum position at t equals 0. So if you did not do that, if you have a different initial condition, like you kick it from 0 and get it with some initial velocity, then you can introduce a phase constant, phi sub 0. So it turns out that x is equal to A times cosine of omega t plus phi 0 is also a solution. Okay, so A and phi are arbitrary, and omega is equal to square root k over m still. And then you've just got v sub x. Again, the phi doesn't really do anything, it just sits in there. I think Vx is just negative A omega times sine of omega t plus phi sub 0. It just shifts the curves back and left and right. And A sub x is negative A omega squared cosine of omega t plus phi sub 0. So those are the actual equations I like to put on my A sheet. We can try to plot it. So here's those same equations again. I've just written them down or typed them in. Let's do black for let's do velocity, Vx versus time. So I've drawn dashed lines. When the position is at a maximum, like it's gone as far as it's going to go, and then it's turning around, that's when the velocity is 0. So that's going to be a zero velocity right there, and also a zero velocity right here. And then for this whole time, it's sort of speeding up and going down, so that's a negative velocity. So I think it's going to go down. It'll have its maximum velocity when it stops accelerating. And then the spring is now pushing it, slowing it down. So it goes kind of like that. And then once again, it's going to hit its maximum up here. Something like that. It's fun to sort of try plotting these. And then if you want to plot a sub x versus t, we'll do that in red. It's the slope of this, right? So when the velocity is maximum, that's when the acceleration is 0, or when the velocity, or minimum or maximum. And then it accelerates, this is positive, so its maximum acceleration is when its velocity becomes 0, something like that. Okay, and that turns out to be like the upside down of that. So that's sort of instructive to try to go through those curves. Okay. Let's see where. Want to try it? Again, sorry it's not typed in. It's a pain in the butt to copy these. This should be in your Learning Catalytics, a question. This is the position graph of a mass on a spring. So it's doing this. X equals 0 is the equilibrium position of the spring. So it starts off at maximum. It oscillates like this. So at this instant of time, t, indicated by the dashed line, what can you say about the velocity and the force? Either A, velocity is positive, force is 0. B, velocity is negative, force is 0. C, velocity is negative, force is to the right. D, velocity is 0, force is to the right. Or E, velocity is 0, force is to the left. So think about the force and the velocity at this time instant t, or time instant by the dashed line. I'll give you a minute. Yeah, so I basically think this is the time when it is at its maximum to the left of equilibrium position. So the mass is going to be somewhere over here. And so there's going to be a big force to the right. F is going to be pushing, the spring will be pushing, so it's going to be one of these two. And also it's going to stop at that point because it's turning around, so I think it's D. That's the answer. Okay, and then let's do another one. Very similar. Make sense? This is the x is the most negative it is, so it means it's to the left. What if you have x right at the equilibrium? But, and also, it's not just, it was at the left, and now it's passing equilibrium and it's going to the right. Give you a minute. Okay, 91% of you got those A, which I think is right. So it's going on the way up. That means that it's actually moving towards the right at that instant. So there's two ways it can be at equilibrium, either moving to the left or to the right. But at this point, the slope is positive, so it's moving to the right. And also the force will be 0 because the spring is at equilibrium at that instant. Now here's a tricky one. What is phi? What is this phase constant? And just as a reminder, I've given you this equation. X is equal to omega t plus phi sub 0. Here's x versus t. And I put the fact that, what have I put here? That, oh well. These points 1, 2, 3 are telling you something. This one was a hard one. But it was showing 51% was showing A. So I think what we were looking for is this. But let me try to give you a mathematical way of solving these kinds of problems. You know this. You also know, let's say, for example, at the origin, when t equals 0, we know that x equals plus a over 2. So what we can do is say that, you know that x is equal to a times the cosine of omega t plus phi sub 0. So t is equal to 0, and x is equal to a over 2. So a over 2 is equal to a times the cosine of phi sub 0. So you know the cosine of phi sub 0 is equal to a half. So phi sub 0 is equal to cos to the negative 1 of 0.5. Okay, so then you have to kind of be a little careful. If you just plug it into your calculator, you'll get 60. But it's good to think about that a little bit. It's either plus or minus 60 degrees, I think. So if this is cos, and this is phi, this is cos of phi sub 0. You have to remember that there's this sort of ambiguity. It's plus or minus. Phi sub 0 equals plus or minus 60 degrees. Don't forget to times it and change it into radians, so you can do pi over 180, and you get plus or minus pi over 3 radians. And then I'm going to choose the minus solution. Because we know that it's going upwards. So your function cosine has to be on the way up, not on the way down. Okay, since x is increasing. So it's a little difficult to figure out that. Usually use the second derivative actually. You'll use v is equal to negative a omega, and then that resolves that sign ambiguity.
So x is decreasing, that would be positive.
Yeah, if x was decreasing, then the whole thing would be shifted over, and you'd be plus pi over 3. Let's look at some of the pre-class quiz results from this morning. An object is executing simple harmonic motion. What is true about the acceleration of this object? Well, the acceleration is maximum when the displacement is a maximum. That's true. The acceleration is a maximum when speed is a maximum. That's not true. It's actually, the speed is a minimum at the ends. Acceleration is maximum when the displacement of the object is 0. No, that's when the acceleration is also 0, because there's no force at that point. Acceleration is 0 when the speed of an object is maximum. Right, that's when it's passing its equilibrium. So the spring is actually going as fast, the mass is going as fast as it will go when it passes the equilibrium of the spring. Acceleration is a maximum only when the object is instantaneously at rest. Right, so at the max and min positions, it stops for a minute, but it's got its maximum force. So that was good. This question 2 was, in simple harmonic motion, the speed is greatest when the magnitude of the acceleration is a minimum. And then I had someone ask me about, to solve this one out, let's do it. A sewing machine needle moves up and down in simple harmonic motion with an amplitude of 1.7 centimeters. So you've got SHM. You've got A is equal to 1.27 centimeters. So I should convert that to SI units, 0.0127 meters. That's your amplitude. And a frequency of F is equal to 2.55 hertz. We need to convert that to SI units as well. So omega is equal to 2 pi times F. So it's equal to 2 times 3.14159, whatever, times your 2.55. And you get omega is equal to 16.02211 radians per second. And then your V max is equal to A times omega. So 0.0127 meters, all times for 16.02211 radians per second. And the issue there is that radians, being the magical unit that they are, just go away. The leprechaun took away the radians, and you end up with 0.203 meters per second. That's how I did that one. I'll scan that in later. Some pre-class comments. Yay, more calculus. I couldn't agree more. I mean, it's so beautiful. Okay. I think it might have been sarcastic, I don't know. Do we need to know how to get the formula x equals a times cosine omega t plus phi? Well, I don't know how to get that. It was a trial solution. I'm not sure where it came from, actually. I've been wondering that for the last 20 years, so just let me know if you figure it out. What is the difference between angular frequency and angular velocity if they are both represented by lowercase omega? I had a bunch of people ask me that question, and I think the answer is simply context. They're very different. They're both in radians per second, but one is talking about you've got a spinning wheel, and maybe any point on the spinning wheel has an angular velocity. And the other one is you've got a mass on the spring just going back and forth. There's no turning or rotation at all. That's just 2 pi over t. Anyway, and then how do we get Vmax and Amax? So remember, these are the equations. V equals negative omega times A times sine, and A is negative omega squared. We found that from the trial solution. So you can find out Vmax and A max by just setting either sine or cos to be negative 1. Because sine and cos vary between +1 and negative 1. And so that's your max will just be, just cover them up. Make sense? Comes from those equations. Okay. So here's something, and we'll do a little demo of this. The frequency is set by the properties of the system. In the case of a mass attached to a spring of spring constant k, the frequency is always 1 over 2 pi times the square root of k over m. That's just saying it's 1 over 2 pi times omega, and omega is square root of k over m. A and phi are set by the initial conditions, which would be like the initial position, x sub 0, and the initial velocity, v sub 0. And A also turns out to be related to the total energy. We'll talk more about that on Wednesday. Can we switch, Kevin, to this one? So, just example, this is going to be vertical simple harmonic motion, but it's similar to horizontal. It's just very difficult to set up a frictionless surface, so I'm going to do it vertically. Here we have the same mass. M is, I think, 200 grams in both these cases, and they're hooked to 2 different springs. And this spring seems to be a little more stretchy than this spring. See how this one goes down a little further? So I think this one has the lower spring constant. And then if you pull it down and release it, I'm getting a little confused. Let's release it from lowest and then let it bounce. Yeah, this one's bouncing up and down a little faster. The one on your left, a little faster than the one on your right. Now, there's also swinging. Let's not do swinging. Let's be a little more careful here. Let's pull it directly down and get it going up and down. So different spring constants means different oscillation frequencies. Now, if I just put this over here. Yep. There we go. A little bit further out. Perfect. Now, what I have is the same spring. If I release them together, they oscillate together. Same spring constant, same mass. But I can change the mass. I can double this mass by hanging one underneath. It's escaped. Okay. Luckily, we got Kevin. I'm a little clumsy here. So then, attach double the mass. Whoa, it goes way down. Still on the screen. And now once again, release it. Let go. And now this one is oscillating with a much lower frequency because mass is on the denominator of that equation. More massive object with the same spring constant, you get a lower frequency. So point being, and you can see on the side screens, the frequency is not at all arbitrary. It's not at all set by the initial conditions. I could release it a little bit, I could hit it, I could release it a lot. Doesn't matter. As long as Hooke's law is obeyed, the frequency is always set by the physical properties of the system. Thank you. So this might be getting a little obsessive with learning catalytics, but which of the following quantities in the description of simple harmonic motion is not determined by the initial position and velocity? So if you're just listening, give you 1 minute. 60% of you, I believe, got this one. So angular frequency always equals the square root of k over m. Has to. You find a spring constant, you have a mass. There are other things. There's a pendulum, which is what we'll talk about on Wednesday. Then you have the gravitational constant, you have the length of the pendulum. That will determine omega. Omega is always determined by the properties of the system. It doesn't matter how hard you kick it, how much energy it contains. If it's simple harmonic motion, omega is going to be fixed. Okay? And initial position and velocity don't change it. So, another question. Okay, a mass is oscillating on a spring in simple harmonic motion. When it passes through its equilibrium point, you give it an external kick, which suddenly decreases its speed. But not to zero, so it continues to oscillate, but just at a lower amplitude. As the result of this slowing, the frequency of the oscillation A goes up, B goes down, or C stays the same. Be 1 minute. Okay, survey says, it's a little better on this one, but...
Oh, see! I told you! I told you! I told you!
Okay, guys, I'm using the other side of the Sharpie, okay? Doesn't matter. You kick it, it slows it down, speeds it up, okay? As long as Hooke's law is obeyed. The only way it could change is if there was dirt in your shoes, it changes the mass. Or maybe you stretch the spring so much that it no longer obeys Hooke's law. And so it's no longer simple harmonic motion. So I don't know if you've ever played with your slinky at home, but the slinky obeys Hooke's law for a while until you give it to a 3-year-old, and then they overstretch the spring. It no longer obeys Hooke's law, and you don't get simple harmonic motion. So that's why you never give a slinky to a 3-year-old. So last thing I do want to quickly go over is vertical mass on a spring. We showed it here, and it looks really complicated because now there are two forces on the object. There's the upward spring force, which is going to be k times x, where x is now down or something. At least we know that the magnitude of that will be upwards, k times x. And we've got the weight, which is magnitude of that is mg. And then we have the unstretched spring and the new equilibrium position. So this is the new equilibrium position of the mass will be when kx equals mg. And this x here, x equals delta L. So x was measured from here, so you get k times delta L equals mg, and it's delta L is equal to mg over k. So that's where the mass would hang if it were not moving. Like if I stopped all the oscillation on these things, it stops at a position. It doesn't stop at the spring's equilibrium, it stops below that, right? Where the force, upward force equals the downward force. And then you just get simple harmonic motion around that. It takes a little bit to prove it. But you set y equals 0 to be the block's new equilibrium. And then you have y is equal to a times cosine of omega t plus phi sub 0 is your trial solution. And omega is equal to k over m square root. So you get oscillation around the position. It turns out to be symmetrical. The only effect of gravity, and this is proved in Wolfson, is to just shift the equilibrium position downwards. And so the vertical spring is very similar to the horizontal spring. Instead of oscillating, though, around the spring's equilibrium is some high point, you're oscillating around the block's equilibrium. So you can finish up chapter 13. We'll finish it up on Wednesday, or you can watch this pre-class video. Something to think about over the weekend. If you have a pendulum swinging back and forth, and you double its mass, does it change the frequency? We know that it changes the frequency of a mass in a spring if you double a mass. What if you double the mass of the pendulum? Does it slow it down? And I'll see you Wednesday.